Dangayach to introduce her and congratulate her on this grant, and then she's going to tell us in a few minutes about what her project is.
This is just a congratulations to someone everyone knows in the department. Ray's in her final year of training with a lot of protected time this year for research, and has been awarded an internal Mount Sinai grant for a project that will use artificial intelligence to basically evaluate patients in an automated fashion using image detection and video analysis to correlate their neurologic function to what's being seen essentially on camera. Many of us know that video EEG and other video modalities are increasingly commonly used in clinical care, but are, while they're very, very data rich, are not really mined for the full extent of what is contained in the video stream. So Ray has proposed a project to use all the modern suite of video analysis tools that are used in other domains of image recognition and other fields beyond medicine, trying to bring that into neurocritical care and neurosurgical care. Very, very excited to see where that goes. And I'm not sure, Ray, if you have one of your demo videos to show this morning, but if not, then looking forward to sharing it with the group in a future green rounds.
Yeah, I have some gifts to show to everyone briefly. And then I'm going to share my screen.
And I'll just say a couple of things about this project and how Ray has really come into her own as a brilliant surgeon, as a brilliant human being. She's one of those people who I'll reach out to for a smart person consult. So I'm so excited to serve on her mentorship team. One of the things about this grant was developing a transdisciplinary project, and Ray has taken that to the next level, taking inspiration, like Ben said, from how video analysis is performed in other fields other than medicine, and how we can leverage that in performing a more objective neurological examination in the neurocritical care world. So thank you, Ray, and over to your presentation. Very excited to see what you're going to share with the group.
Thank you so much, Dr. Dangayach, and thank you for the really kind introduction to Dr. Rapoport. Really appreciate you guys being so supportive and serving as my mentorship team. So yeah, like we just mentioned, I'm gonna quickly talk about my project. It's titled Explainable AI Post-Tracking to provide a continuous neurological exam in the NSICU. And where does this come from? Well, essentially is we all rely on the neurological exam. It's so crucial to what we do on a daily basis in terms of assessing patients. It indicates their progression. It really drives our decision-making to see whether or not a patient needs intervention. And also it's a key reason for us to escalate a patient to the neurointensive care unit because they need a QI-hour neurochecks. And our ability to continuously quantify this extremely important parameter right now is very limited. Like I said, even when patient goes to the NSICU, at best they're being neuro assessed at Q1-hour basis. And also this assessment can be highly subjective depending on the interviewer. And it may not pick up the subtle and subacute changes. I think we all had the experience of putting a patient on clamp trial, for example, and then not really being able to determine if they're subtly more sleepy than pre-clamp trial, and also if they're altered, or whether or not that's from the interviewer not using the correct language, or we just arouse them from deep sleep. So we all have been in that situation where it was just very inconclusive, and maybe three person are all getting a different exam from the same patient. So this is really an unmet need. But on the other hand, we have a lot of data. We have a lot of videos on these patients that are already available. From our unit, they're mainly coming from video EEG data, But in a lot of other units, there are also wall-mounted cameras, ceiling-mounted cameras, or just like patient monitoring cameras that are constantly picking up this data that's really not being used right now. So that led us to really want to put this together. We want to use Pose AI, which is a method that tracks movement, and it has already shown promising results used in the athletic world. Elite athletes commonly use it to track their own movement and posture and to see how they can improve their form. So similarly, we think that it can be used to track patients in the NSICU. And Mount Sinai actually already has some development with this technology being used on babies in the NICU. So this is glancing over our methods. We're going to collect data. We're going to run it through our Pose software, and then we're going to try to predict, quantify the patient's movement, and then use it to predict other clinical parameters. So we already started this with one single patient. We collected video EEG data from this patient. That's from the NSICU. We have 2 episodes of this patient being on video EEG, and we randomly chose 2-minute clips from each of these episodes. And we're correlating this with the patient's RASS scale, which is a scale of how agitated they are and how agitated or sedated they are. And we're essentially using this as a proof of concept. On the right-hand side, you can see like the red dots are at the points where we have the patient on video EEG. And if you look at the RASS scale on the top, one period lands on where the patient has a RASS of -4, and the other one has a time period has a patient at a RASS of 0. So this is a quick reminder of what the RASS scale look like. -4 is essentially when the patient is under deep sedation, no response to voice, but there is some movement or eye opening to stimulation, where 0 is kind of a baseline where the patient is awake and spontaneously paying attention. So this is what that actually looks like. This is the period of when the patient is at a RASS of 0. As you can see, this patient is able to spontaneously move their arms. And the software is picking up all these key points on her body, like where her hand is, where her elbow is, and where the knees are, and tracking its movement throughout the scene. And this is when this patient is more deeply sedated. And this is the graph just illustrating the patient's movement in X axis and also Y axis. And then, as you can already see, there's a wider range of movement for this patient when they are having a RASS of 0 versus -4. And that's true for the X coordinate as well as the Y coordinate. This is another illustration of a similar data that the patient has a more variable movement index when they are having a RASS of 0 versus -4. So what we're concluding from this very preliminary data, that it's quite possible to use this Pose algorithm to differentiate light versus deep sedation in this one single patient. And we potentially would love to develop this technology into a monitoring modality that can be akin to cardiorespiratory telemetry. And also it can possibly be scalable to an even more diverse range of settings, including the stroke floor, rehabilitation centers, nursing home, even non-healthcare related facilities. So what are the next steps we're taking this project? We definitely want to correlate our movement index with other clinical parameters and neurological changes. For example, vital signs, intracranial pressure, pain score, age, stroke scale, TCD values, etc. And we also want to start prospectively collect data. So we're working on IRB with that right now. And we also want to improve our camera source data. First of all, even with wall-mounted cameras, that will help us not just limit our data source to patients who are on video EEG, and also they're less likely to be bumped or redirected. And we also can consider using IR cameras, which can pick up heat signals, and that's useful for patients who are under covering or are or at night with low light settings. And also there are cameras that can pick up depth, so that will give us a 3D movement measurement rather than just 2D. And other things, interesting things we can consider, for example, like facial feature tracking that looks at comatose patients maybe and see their eye opening, eye movement, facial expression, etc. Yeah, so there's a lot of different routes we can still take this technology. And my goal is to be able to use this protected time to be able to generate sufficient data for the next step in the NIH training grants, for example, K awards, R awards, etc. So thank you very much. I really want to acknowledge Dr. Dangayach and Dr. Rapoport for being such incredible supportive mentors, and also Felix Richter, my close collaborator, for helping me put this together.
Awesome. Looking forward to see where this goes over the course of the year. It's very exciting work.
Very exciting work. You can see in chat today, Jeremy said you should come over to the dark side for spine, but I think we can totally use Pose AI to track movements.
Is there a way to anticipate that they're going to be covered with blankets? And, you know, if this becomes useful, maybe even the way we cover patients and keep them warm would change, because you want access to their limbs if you're going to be tracking movement. So there might be some way to adapt the clothing or some sort of suit or something that would work.
Yeah, for sure. That definitely is a potential problem in terms of the video capture. So yeah, I spoke with Dr. Dangayach about it, potentially just keeping the room warmer without needing a blanket for the patient, and also potential like IR camera, which can still pick up like the heat signal from the patient's body even while they're under maybe like a thin blanket. So we have some thoughts and ideas about that.
Yeah. Or maybe a bracelet, certain type of bracelet around the ankles and wrists that would hold a sensor, that, because it's really just a point on their limbs you're looking for, isn't it?
Yeah, exactly.
Well, this is a really interesting project.
Thank you, Ray, and congratulations.
Thank you so much.